What if you could step onto a piece of our planet that has been here since before there was a single breath of oxygen in the air, before the first stirrings of life, before continents, as we know them, even existed? This isn't science fiction, it's real. Just beneath our feet, in one of the most remote corners of the world, lies the oldest Flaw on Earth, a vast and ancient surface that has remained largely unchanged for 4 billion years. To stand upon it is to touch a moment in time so distant, so profound, that it redefines your understanding of history itself. This is more than rock. It's a living record, a time capsule written in stone, holding within its layers the story of our world's fiery birth and its long, patient journey toward becoming the planet we call home. In this video, we're going to do more than just talk about this geological wonder. We're going to walk across it together, tracing a path that stretches back further than life, further than oceans, further than the moon itself. We'll uncover how this incredible surface formed during Earth's most violent and chaotic era, a time of searing heat and constant bombardment, when the very ground beneath our feet was still taking shape. We'll reveal how scientists confirmed its staggering age using some of the most advanced technology ever developed, and what these ancient stones can teach us not only about where we've been, but where we might be headed. This journey is about connection not just to Earth's past, but to something bigger, the awe that comes from confronting deep time, and the humility of recognizing our small but meaningful place within it. Whether you're passionate about science, history, adventure, or simply curious about the world's hidden wonders, there's something here for you, so come with us. Let's explore this primordial landscape, unlock the secrets buried in its billion-year-old silence, and discover what it truly means to walk across a surface that has witnessed the entire history of our planet. To truly grasp the magnitude of what it means to walk across a surface 4 billion years old, we need to rewind the clock to the very beginning of our planet's story, to a period so hostile and alien it's known as the Hadean Eon. This era, named for the Greek underworld, Hades, was a fitting title for a world that was essentially a hellscape of unimaginable violence. The Earth was a newborn planet, freshly coalesced from the dust and debris circling the young sun, and it was a cauldron of molten rock. The surface wasn't solid ground as we know it. It was a global ocean of seething magma, constantly churned by immense heat from within, and battered from above by a relentless rain of asteroids and protoplanets. One of these colossal impacts was so tremendous it is believed to have sheared off a piece of our planet, creating the moon and melting the Earth's surface all over again. It was in this apocalyptic furnace that the story of our oldest Flaw begins. As the planet gradually began to cool from its fiery birth, the first solid skin started to form on that bubbling magma ocean. Imagine the surface of a pond beginning to freeze over, but on a planetary scale and with rock. Minerals with the highest melting points, like zircon crystals, were the first to solidify, creating tiny, durable seeds of stability. These microscopic time capsules began to aggregate, and through a process called fractional crystallization, the very first patches of proto-continental crust, known as cratons, started to nucleate. This wasn't a smooth, uniform process. It was stop and start, with new molten rock constantly welling up, and asteroid impacts frequently shattering the fragile, thin crust, melting it back into the global stew. The incredible survival of the Acasta Gneiss is a testament to finding a safe harbor within this chaos. This rock didn't form in a vulnerable, thin layer on the surface. Evidence suggests it crystallized deeper within that early, unstable crust, protected from the worst of the surface bombardment. Its composition points to an origin as a granitic rock, which requires the presence of water to form, hinting that our planet's water may have arrived much earlier than we once thought. This wasn't just any rock solidifying. It was a piece of continental crust in its most primordial form. For it to survive, it needed to avoid being recycled back into the mantle by the nascent, violent motions of early plate tectonics or being vaporized by another planet-altering impact. It found a stable niche, a quiet corner in a furious world, and it held on. Its endurance gives us a physical point of reference, a singular place where we can point and say, "Here." This was here when everything else was chaos. This resilience, born from a specific set of circumstances in Earth's most violent chapter, is what allows us today to literally stand upon the foundation of the ancient world. So where on our dynamic, ever-changing planet can such an ancient relic possibly survive? You might picture a hidden, inaccessible mountain peak or a deep, unexplored cavern, but the truth is both more remote and more grounded. The oldest Flaw on Earth is found in the vast, wild expanse of the Canadian Shield, a massive geological structure that forms the ancient heart of North America. More precisely, it lies within the Acasta Gneiss complex, a specific outcrop nestled in the remote wilderness of the Northwest Territories near the Arctic Circle. This is not a place you stumble upon by accident. It is a destination reached only by deliberate and often difficult journey, a pilgrimage for those seeking to connect with the deepest chapters of our planet's story. The Canadian Shield itself is a breathtaking landscape of raw, primordial beauty. Imagine a sprawling expanse of bare rock, scoured smooth by ancient glaciers, interspersed with countless freshwater lakes and dense boreal forest. It is a land of silence and scale where human presence feels fleeting. This region is what geologists call a craton, a stable, ancient core of a continent that has escaped the destructive forces of plate tectonics for billions of years. While the edges of continents crumple and fold in mountain-building events, and ocean floors are constantly recycled back into the mantle, the craton remains a steadfast anchor. It is a geological vault, and the Acasta Gneiss is its most precious treasure, locked away in a stable interior far from the tectonic turmoil that has reshaped the rest of the world. The preservation of these rocks is a story written in stability and climate. Tectonically, this craton has been a quiet neighbor for eons. It hasn't been involved in a major continental collision or ripped apart by rifting in over 2.5 billion years. This incredible stability meant the rocks were never shoved deep underground to be melted and recycled, nor were they pushed up into high, eroding mountain ranges. They have, for the most part, simply stayed put. Furthermore, the climate of the far north has acted as a perfect conservator. The cold, dry conditions significantly slow down the chemical and physical processes of weathering that break down rock. The landscape was also scraped clean and polished by massive ice sheets during the last ice age, which had a dual effect. It removed younger, overlying layers of sediment and soil, effectively peeling back the curtain to reveal the ancient basement rock beneath, while the ongoing cold helps keep it exposed and intact. Getting to this specific site is an expedition in itself. The Acasta Gneiss outcrop is located approximately 300 kilometers north of the city of Yellowknife. There are no roads that lead there. Access typically involves a small charter plane or a helicopter flight over a stunning mosaic of lakes and evergreen forests, a journey that underscores the site's profound isolation. This remoteness has been its silent guardian, protecting it from development and mass tourism, preserving it for careful scientific study. The very difficulty of reaching this place adds to its aura, making the act of standing on that 4-billion-year-old surface not just a scientific observation, but a hard one and deeply personal experience of connection with deep time. So how do we move from knowing a rock is incredibly ancient to assigning it a specific, mind-boggling age of 4 billion years? The answer lies in a remarkable natural process that turns certain minerals into precise geological clocks. It all comes down to radioactivity, not as a destructive force, but as a dependable and predictable timer that started the moment these minerals first crystallized from molten rock. Scientists use a technique called radiometric dating, and for rocks as old as the Acasta Gneiss, the method of choice is uranium-lead dating, specifically performed on incredibly resilient minerals known as zircons. Imagine a zircon crystal as a tiny, nearly indestructible time capsule. When it forms in cooling magma, its crystal structure readily incorporates atoms of uranium into its lattice, but it strongly rejects atoms of lead. This is the crucial starting point. It means that when the crystal is born, it contains a measurable amount of uranium but essentially zero lead. However, uranium is an unstable, radioactive element. Over immense periods of time, it spontaneously decays at a fixed and known rate, transforming into lead through a series of intermediate steps. This isn't a random process, it's a statistical certainty. Each type of radioactive isotope has its own unique half-life, the time it takes for half of the parent atoms in a sample to decay into daughter atoms. For the uranium-238 isotope used in dating the oldest rocks, that half-life is about 4.5 billion years, a timescale perfectly suited for measuring the age of our planet. The science, therefore, becomes a matter of precise measurement and careful detective work. Geologists first must extract these tiny zircon crystals from the rock, which is a painstaking process of crushing, grinding, and separating minerals by density. A single sample might yield only a few usable grains. Then, using incredibly sensitive instruments called mass spectrometers, they vaporize tiny spots on these crystals with a laser and measure the exact ratio of remaining uranium atoms to the accumulated lead atoms. Because we know the decay rate is constant, this ratio is a direct readout of time. If half the uranium has decayed into lead, the crystal is 1 half-life old. If 3/4 have decayed, it's 2 half-lives old, and so on. By measuring these ratios with extraordinary precision, scientists can calculate the exact amount of time that has passed since that zircon crystal first solidified and locked the uranium atoms inside its structure. Of course, working with such ancient materials comes with significant challenges. The primary concern is contamination. Has the crystal been heated or disturbed by a later geological event, potentially causing some lead to leak out or new uranium to seep in? To account for this, scientists don't just take one measurement. They analyze multiple zircons from the same rock and even multiple spots within a single crystal, building a statistical spread of ages. They also use a cross-checking method involving 2 different uranium isotopes that decay to different lead isotopes at different rates. If both of these clocks read the same age, the date is considered highly reliable and concordant. The oldest dates from the Acasta Gneiss, consistently clustering around 4 billion years, have passed this rigorous test, giving us the confidence to point to that specific outcrop in Canada and declare it the oldest known place on Earth. It's a testament to human ingenuity that we can hold a piece of that rock and, by reading the atomic story written inside it, peer directly into the dawn of our world. But what exactly is this rock that has endured for almost half the lifetime of the universe? The Acasta Gneiss is far more than a simple, ancient stone. It is a complex and beautiful archive, its very fabric telling a story of unimaginable endurance and transformation. The term gneiss itself is key to understanding its character. Gneiss is not a specific mineral, but a metamorphic rock defined by its distinctive texture, a banded or foliated appearance, like a layer cake of light and dark minerals that have been stretched and folded under titanic forces. This tells us immediately that the rock we see today is not in its original, pristine form. It has been through the geological wringer. The story begins over 4 billion years ago when the precursor to this rock, likely a granitic-type rock, first crystallized from a cooling magma body deep within the young Earth's crust. This original rock, known as the protolith, was then subjected to an epic sequence of events. Over the eons, it was buried deep underground, subjected to immense heat and pressure that would have softened it, making it pliable. It was squeezed and stretched by the movements of the early Earth's crust, a process that aligned its minerals into those characteristic bands or stripes. This metamorphic event essentially cooked and recrystallized the rock without fully melting it, transforming its texture and appearance while preserving the chemical evidence of its original, ancient age. It's like taking a piece of clay, pressing it, heating it, and twisting it. It changes form, but the material itself remains. The visual texture of the Acasta Gneiss is a direct map of this incredible journey. When you look at a sample, you see swirling, interleaved bands of light-colored minerals, primarily feldspar and quartz, and dark-colored minerals like hornblende and biotite. These dark and light layers are the result of different minerals separating and migrating under extreme heat and pressure, a process called metamorphic differentiation. The patterns, sometimes tight and parallel, other times wildly contorted, record the direction and intensity of the forces that acted upon it. It's a frozen snapshot of a dynamic, violent past, a sculpture crafted by the very forces that build continents. Scientists study this rock like detectives, analyzing a crime scene with 4-billion-year-old evidence. In the field, they meticulously map the orientation of the foliation, measuring the dip and strike of the mineral bands to understand the direction of the ancient pressures. Back in the laboratory, they use powerful microscopes to examine thin sections of the rock, slices so thin that light can pass through the minerals. Under polarized light, they can identify each mineral crystal, see how they interlock, and observe tiny imperfections that reveal the stress the rock endured. Most importantly, they hunt for the real treasure, zircon crystals. These incredibly durable minerals often survive the metamorphic process intact, preserving their original uranium-lead clock from the initial crystallization event. By dating these resilient zircon time capsules, researchers can peer through the later metamorphic overprint and directly date the rock's first formation, confirming its status as the oldest known fragment of our planet's crust. The Acasta Gneiss, therefore, is not just a single-page document. It is a palimpsest, a parchment on which the original text from 4 billion years ago is still faintly visible beneath the profound and dramatic rewriting of 2.5 billion years of metamorphism. It defies time not by remaining unchanged, but by recording every chapter of its long, incredible existence. To actually step onto the Acasta Gneiss is an experience that transcends simple geology. It becomes a deeply personal and sensory conversation with deep time. The first thing that strikes you is the profound silence, a stillness so complete it feels like a physical presence. You are hundreds of kilometers from the nearest town, surrounded by the vast, untouched wilderness of the Canadian subarctic. The only sounds are the whisper of the wind sweeping across the barren rock and the distant cry of a bird. This isolation immediately strips away the noise of the modern world, creating a mental space where the enormity of the place can truly sink in. Then you look down. The rock beneath your boots is not a smooth, uniform slab. It is a complex tapestry of textures and colors, a landscape in miniature. Your fingers trace the alternating bands of pale gray feldspar and dark, glittering hornblende, feeling the undulating grooves and ridges carved by billions of years of erosion. The surface is cool to the touch, even on a sunny day, holding the steady, low temperature of the deep earth from which it came. It is rough and gritty, weathered by countless freeze-thaw cycles, scoured by glaciers, and polished by the faint, patient caress of wind and rain. Every step you take connects the soles of your feet to a surface that solidified when our planet was an infant, a mere 500 million years old. This very spot witnessed the Great Bombardment, the formation of the first oceans, and the slow, patient journey toward a habitable world. There were no plants, no animals, not even a single-celled organism to witness its formation. The air was thick with toxic gases, and the sky, devoid of oxygen, would have glowed a dull, ominous red. This sensory input culminates in a cognitive shift, a feeling often described as a sense of deep time. It's the humbling, almost dizzying realization of your own fleeting existence against a timeline that is almost incomprehensibly vast. Your entire life, the entirety of recorded human history, every war, every discovery, every work of art, all of it is less than a blink of an eye compared to the lifespan of the rock you are standing on. This perspective is not frightening, it is strangely grounding. It evokes a profound sense of awe, a quiet reverence for the resilience of our planet. You are not just a visitor to a remote location. You are a momentary witness to a story that began long before you and will continue long after. It invites a quiet reflection on our place in the cosmos, not as the center of the universe, but as a conscious part of an ancient, ongoing, and magnificent planetary saga. The experience leaves an indelible mark, a memory not just of a place, but of a feeling the weight of history and the quiet, enduring strength of the world beneath our feet. But the significance of this ancient flaw extends far beyond its staggering age. It serves as a foundational text in the grand story of our planet, a physical dataset that allows scientists to test and often rewrite long-held theories about Earth's infancy. Before the discovery and confirmation of the Acasta Gneiss's age, many models of the early Earth depicted the first half-billion years as a completely molten hellscape, a period called the Hadean where no substantial crust could possibly survive. The existence of this 4-billion-year-old rock fundamentally challenged that view. It provides the first direct, tangible evidence that stable continental crust began forming much earlier than previously believed, perhaps as early as 4.4 billion years ago. This discovery forces a dramatic revision of our planetary timeline, suggesting that the Earth cooled from its molten state and developed a solid shell far more quickly than we ever imagined, transitioning from a ball of magma to a planet with recognizable landmasses in a relatively short geological window. This rock is also a crucial piece of evidence in one of geology's greatest debates. When did plate tectonics, the engine that drives our dynamic planet, first begin? The twisted, folded, and metamorphosed nature of the Acasta Gneiss tells us that enormous forces were at work reshaping the crust not long after it formed. Some scientists interpret this as evidence for a very early, more vigorous form of plate tectonics, while others propose different mechanisms, like a stagnant lid regime where the crust moved in smaller, more local ways. By analyzing the pressure and temperature conditions recorded in the rock's minerals, geologists can reconstruct the tectonic environment of the time, using this single outcrop to test competing models for how the young Earth's machinery actually operated. It's a key that helps us unlock the geological processes that set the stage for everything that followed. Furthermore, the chemical signature locked within the Acasta Gneiss offers tantalizing clues about the conditions that may have led to the spark of life. The rock's original granitic composition suggests the presence of water deep within the Earth's crust at this incredibly early date. Water is, of course, the universal solvent and an absolute prerequisite for life as we know it. This implies that our planet was cool enough and wet enough, at least in its subsurface, to create the kind of stable, aqueous environments where probiotic chemistry could potentially begin. While the rock itself does not contain fossils, it paints a picture of a world that was becoming increasingly hospitable, moving away from a perpetual inferno toward a state where the building blocks of life could eventually assemble. It helps define the boundary between a purely abiotic world and one poised on the brink of a biological revolution. The value of this site also lies in its ability to help us understand Earth's place in the solar system. By providing a firm date for the formation of early crust, it helps us calibrate the timeline of the late heavy bombardment, a period when the inner planets were pummeled by asteroids. If this crust was already stable and largely intact 4 billion years ago, it must have somehow survived this cosmic onslaught, informing models about the intensity and duration of that violent period. Every sample taken, every isotope measured, and every mineral analyzed from the Acasta Gneiss adds a critical data point to our understanding of planetary formation and evolution, making this remote outcrop in Canada not just a piece of local geology, but a reference point for understanding rocky planets across the cosmos. While the Acasta Gneiss holds the title for the oldest known intact expanse of bedrock, it is far from the only window into our planet's deepest past. To truly appreciate its significance, we need to place it on a global stage, comparing it to other ancient geological sites that each tell a different part of Earth's early story. Think of it not as a single record, but as one crucial chapter in a scattered planetary archive. Other locations, like the dramatic landscapes of Greenland and the sun-baked outcrops of Western Australia, preserve rocks and minerals of a similar, breathtaking antiquity. Each of these sites has survived through a different set of geological circumstances, and each one offers a unique type of evidence, helping scientists piece together a more complete and nuanced picture of the primordial Earth. One of the most important comparisons is with the Isua Greenstone Belt in southwestern Greenland. The rocks here are also phenomenally old, dating to around 3.8 billion years, making them slightly younger than the Acasta Gneiss, but arguably even more revealing. The key difference lies in their story. While the Acasta is a metamorphosed granitic rock formed deep within the crust, the Isua rocks are greenstones, metamorphosed volcanic and sedimentary rocks that originated at or very near the Earth's surface. This is a monumental distinction. The presence of sedimentary rocks like banded iron formations implies the existence of large bodies of water and ocean at that time. Even more astonishingly, some rocks in the Isua belt show a peculiar isotopic signature, a fingerprint that some scientists interpret as the earliest indirect evidence of life. The carbon isotopes found there suggest biological processes may have been at work, potentially from microbes that lived around hydrothermal vents. So, while Acasta shows us the stage, the early continental crust, Isua gives us hints about the first possible actors on that stage, offering a glimpse into the chemical processes that may have led to life itself. Then we travel to the Jack Hills of Western Australia, a site that presents a fascinating paradox. The bedrock here is much younger, but embedded within it are tiny, resilient mineral grains that are even older than the Acasta Gneiss itself. These are zircons, the same time-keeping crystals used to date the Canadian rocks. Some of these Australian zircons have been dated to an incredible 4.4 billion years old. This means we have individual minerals that are older than the oldest known rock. How is that possible? These zircons are like geological orphans. They formed in rocks that have long since been destroyed by erosion and tectonic recycling. These parent rocks were ground down into sand, but the incredibly tough zircon crystals survived the process. They were then washed away, eventually becoming incorporated into much younger sedimentary rocks that now form the Jack Hills. So, while Acasta gives us a preserved piece of the original building, the Jack Hills zircons give us a handful of bricks from a structure that no longer exists, providing evidence that continental crust was forming a mere 150 million years after Earth itself accreted from the solar nebula. This global comparison is what allows geologists to move from isolated facts to a coherent narrative. The Acasta Gneiss is the anchor, the oldest surviving piece of real estate. The Isua Greenstone Belt provides the environmental context, suggesting a world with oceans and the potential for life very early on. The Jack Hills zircons push the timeline for crust formation back even further, hinting at a cool early Earth, where conditions may have been stable enough for liquid water much sooner than the hellish Hadian name implies. No single site tells the whole story. Acasta's incredible preservation is unique, but its true power is unlocked when read alongside the chapters held in Greenland and Australia. Together, they form a distributed library, with each location safeguarding a different volume of Earth's autobiography. Understanding their differences in age, rock type, and the specific clues they hold allows us to appreciate that the quest to understand our planet's origin is a global jigsaw puzzle, and the Acasta Gneiss is simply the most ancient and foundational piece we have found so far. This relentless geological recycling is precisely why the existence of the Acasta Gneiss is so extraordinary. It survived because it found refuge in one of Earth's most exclusive and stable neighborhoods, a craton. Think of a craton as the ancient, unshakable heart of a continent, a colossal block of crust that has remained tectonically quiet for billions of years. While the continents around them have flexed, fractured, and foundered, these regions have achieved a state of profound equilibrium. Their deep roots extend hundreds of kilometers into the mantle, making them incredibly buoyant and resistant to subduction, like a massive, unsinkable cork. The Canadian Shield, which cradles the Acasta Gneiss, is the largest and one of the oldest of these geological sanctuaries on the planet. It became a permanent address for these ancient rocks, a quiet cul-de-sac far from the tectonic freeways where crust is constantly being consumed and created. The journey of most crust is a dramatic and finite one. Oceanic crust, for instance, is on a conveyor belt from the moment it is born at a mid-ocean ridge. It spreads outward, ages, cools, and becomes denser, until it is inevitably pulled back down into the mantle at a subduction zone, where it is recycled and ultimately melted. Even younger continental crust is not immune. When continents collide in colossal slow-motion accidents, their edges are thrust upward into towering mountain ranges like the Himalayas or the Alps. While majestic, this process is incredibly destructive to the original rock. The immense pressure and heat metamorphose it beyond recognition, and the subsequent erosion from wind, rain, and ice grinds those mountains down to their roots, washing the sediment into the oceans to begin the cycle anew. Vast swaths of the planet's earliest history have been lost to this relentless geological renovation project. The Acasta Gneiss, however, escaped this fate through a combination of luck and location. After its initial formation and metamorphism deep within the crust, it was gradually exhumed, brought closer to the surface not by violent uplift, but by the gradual, patient stripping away of overlying rock layers by erosion over hundreds of millions of years. It essentially floated to the top of the craton as the material above it was worn away. Once it reached a stable position, the mighty engine of plate tectonics simply passed it by. The continental collisions that built mountains elsewhere, the rifting events that tore landmasses apart, these world-altering events happened around the Canadian Shield, not directly to it. It remained a stable nucleus, a silent witness to the continental drama unfolding at its edges. Its preservation is a testament to the selective nature of our planet's dynamism. For all its power to destroy and recycle, the tectonic system can also create these incredible vaults of stability, saving small pieces of the past for us to discover. This delicate balance between chaos and calm is what allows us to have a direct physical connection to a time that should have been completely erased. Yet this ancient rock's survival is not just a story of deep geological stability. It is equally a tale written by climate. The relentless forces of erosion, wind, water, and ice have the power to grind mountains to dust. Yet in the unique environment of the Canadian Shield, these very forces became unlikely allies in preservation rather than agents of destruction. The key lies in a delicate and fortunate balance. The region's high-latitude location bestows upon it a cold, dry climate for a significant portion of the year. This aridity is a powerful brake on chemical weathering, the process where water, especially when slightly acidic, reacts with rock minerals, breaking them down and transforming solid bedrock into soft clay and soil. In a tropical environment, thick, deep soils would have quickly buried and decomposed the Acasta Gneiss, but here, the chemical reactions that destroy rock proceed at an extraordinarily slow pace, allowing the ancient surface to remain exposed and largely unaltered for eons. The role of ice, however, is the most dramatic and paradoxical chapter in this story. Over the last 2.5 million years, massive continental ice sheets have repeatedly advanced and retreated across North America in cycles of glaciation. These ice ages were not gentle, they were periods of immense geological power. Glaciers several kilometers thick, laden with embedded rock and sediment, acted like colossal sheets of sandpaper, scouring and scraping the landscape beneath them. This process, known as abrasion, can be incredibly destructive, planing down entire mountain ranges. Yet for the Acasta Gneiss, this intense glacial scrubbing had a profoundly beneficial effect. The ice did not just erode, it also excavated. It efficiently stripped away millions of years' worth of accumulated overburden layers of younger sedimentary rock, soil, and vegetation that had built up over the ancient basement. It performed a continental-scale landscaping project, peeling back the earthen blanket to reveal the primordial bedrock beneath. The glaciers essentially cleaned the window into deep time, granting us a clear view of the floor below. The smooth, polished, and striated surfaces found on parts of the shield are the direct fingerprints of this icy activity, a textural record of the ice's direction and power. Wind and water have played their own supporting roles in this epic. The meltwater from those retreating glaciers carved channels and rivers, further cleaning and exposing the rock surfaces. In the millennia since the last ice age, the freeze-thaw cycle has been a persistent but slow sculptor. Water seeps into tiny cracks in the rock, and when it freezes, it expands with tremendous force, gradually prying apart grains and fracturing the surface. While this process weathers the rock, it does so at a glacial pace, pun intended in the cold climate. It creates the rugged, textured landscape we see today, but it hasn't been nearly enough to erase the rock entirely. This interplay between destructive and preservative forces is a fascinating geological dance. The very same processes that have the capacity to obliterate geological history elsewhere, here combined in just the right sequence and intensity to act as curators. They removed the obscuring layers without destroying the exhibit itself. The survival of this 4-billion-year-old surface is a testament to a perfect, and perhaps fragile, alignment of tectonic fortune and climatic moderation, offering a profound lesson on how the history of our planet is not just written in the rocks, but also in the environmental conditions that choose which pages are preserved for us to read. For the indigenous peoples whose ancestors have lived in relationship with this land for thousands of years, the ancient rocks of the Acasta Gneiss are understood not through isotopic ratios or billion-year timelines, but through a profoundly different framework of knowledge and meaning. To the Hadean and Tectonics communities of the Northwest Territories, this is not merely a geological site. It is part of a living, sacred landscape, a place woven into the very fabric of their cultural identity and spiritual understanding of the world. Where a scientist might see a metamorphic rock formed by immense pressure, an elder might see the physical manifestation of a story from the time of the dreaming, a place where the Creator's work is still visible in the stone. The concept of deep time, which science works so hard to quantify, is inherently embedded in their oral histories, which speak of a world being shaped over epochs, connecting people to the land in a continuous, unbroken lineage that stretches back to the beginning of memory itself. This indigenous worldview offers a complementary rather than contradictory path to understanding. Western science excels at answering the how and when, the precise mechanics and chronology of the rock's formation. Indigenous knowledge systems often address the why and who, the purpose and the relational significance of the land. Their wisdom is born from intimate, sustained observation over countless generations, a longitudinal study of place that notes how caribou migrate near certain outcrops, how lichens specific to the oldest rocks are used for traditional medicines, or how the lay of the land tells a story of ancient floods or fires that is passed down through song and ceremony. This knowledge isn't stored in journals. It is carried in language, art, and the shared memory of the community, creating a rich, holistic understanding of the ecosystem that includes its geological bones. Recognizing this profound cultural connection necessitates a paradigm shift in how such a globally significant site is managed and accessed. It moves the conversation from one of simple resource extraction or academic study to one of respectful stewardship and shared guardianship. The growing movement towards collaborative conservation is a powerful model for the future. This involves scientists and indigenous communities working as true partners from the very beginning of any research project. It means seeking free, prior, and informed consent before any expedition is planned, ensuring that community elders and knowledge holders are consulted not as a formality, but as respected colleagues whose guidance is essential. It can involve designing research questions together, so that scientific inquiry can also address issues important to the local community, such as tracking environmental changes or understanding the impact of climate on traditional lands. The goal is to protect this irreplaceable site in a way that honors its dual identity. It is both a world-class scientific archive, crucial to understanding our planet's origins, and a timeless cultural treasure, central to the identity and spirituality of the people who are its traditional guardians. This means implementing protections that go beyond simply fencing off the area. It involves creating protocols that respect the site's spiritual significance, understanding that certain areas might be too sacred for sampling, or that certain times of year may be inappropriate for visitation due to cultural practices. It means training park rangers and researchers in cultural sensitivity, and ensuring that indigenous monitors are present to help guide and inform activities on their traditional land. Ultimately, this approach enriches everyone's understanding. A scientist who takes the time to listen to an elder's stories about the long time ago people of the land may gain a new, more nuanced perspective on the human history of the region, adding another layer to their research. A community that learns about the uranium-lead dating process may find a new appreciation for how their sacred stories align with a scientific timeline of creation, seeing not conflict but a beautiful convergence of different ways of knowing. By weaving these two threads of knowledge together, the empirical and the ancestral, the quantitative and the qualitative, we don't just preserve a rock formation, we honor the full depth of its story. We ensure that the oldest floor on Earth is cherished not only for the secrets it holds about our planet's past, but also for the living culture it sustains and the wisdom it offers for our collective future. Planning an expedition to the Acasta Gneiss is a logistical puzzle that begins months, sometimes years, in advance. It's not simply a matter of booking a flight and packing a bag. It's a meticulously coordinated campaign that balances ambitious scientific goals with the uncompromising realities of the Arctic wilderness. The first step is always securing funding and permissions, a process that involves writing detailed proposals to justify the immense cost and potential risk of the journey. Researchers must then engage in early and continuous consultation with the Tlicho and Dean communities, securing not just formal permits but their guidance and partnership. This is followed by the intricate choreography of arranging charter flights on small bush planes that can land on remote gravel strips or even frozen lakes, coordinating the delivery of fuel and supplies to pre-established cache points, and assembling a field team with the right mix of geological expertise and rugged outdoor survival skills. Every piece of gear, from rock hammers and sample bags to satellite communicators and emergency first aid kits, is weighed and considered, knowing that there will be no corner store for hundreds of kilometers. This phase is a test of patience and foresight, where a single overlooked detail, a missing component for a critical instrument, a misjudgment in food rations, can derail the entire mission before it even begins. The journey itself is an expedition in the classic sense, a multi-stage immersion into one of the planet's last great wildernesses. The team typically flies first to the city of Yellowknife, the last major outpost of civilization, a hub where the buzz of modern life quickly fades. From there, a smaller charter plane carries them north, the landscape below transforming from a patchwork of boreal forest and lakes into a vast, seemingly endless expanse of bare rock and water. The final approach to the site is often the most dramatic leg, sometimes requiring a switch to an even smaller helicopter that can navigate the treeless terrain and land directly on the Precambrian shield. The sensation of stepping out onto the tundra is instantly grounding. The air is crisp and clean, carrying the scent of damp earth and lichen. The silence is profound, broken only by the fading whir of the helicopter blades and the constant, gentle wind. This moment of arrival is always a mix of exhilaration and sobering reality. The sheer isolation is palpable. The team is utterly on its own, with the knowledge that emergency help is hours, if not days, away, a fact that underscores every decision and movement from this point forward. Once on the ground, the delicate work begins, a practice in precision and respect. The researchers are acutely aware that they are visitors in a fragile environment and custodians of an irreplaceable resource. Their aim is to extract the maximum amount of data with the minimum amount of physical disturbance. They start by meticulously mapping the outcrop, using GPS units to record their exact position and high-resolution cameras to document the rock structure and context from every angle. They might use drones to capture aerial imagery, creating a detailed 3D model of the entire site without ever touching it. When it comes time to collect a sample, it is never done cavalierly. The selection of a specific rock is a thoughtful decision, debated and discussed. Using a rock saw or a carefully aimed strike with a geologic hammer, they remove a fist-sized piece, always from a place that will leave the overall appearance of the outcrop intact. Each sample is immediately bagged and labeled with an exhaustive tag noting its location, the rock type, and the date. Even the act of wielding a hammer is done with a sense of reverence. Every chip that flies off is a tiny piece of 4 billion years of history, and the researchers treat it with the care it deserves. The challenges of working in this environment are constant and multifaceted. The weather in the subarctic is notoriously fickle, capable of shifting from brilliant sunshine to horizontal, freezing rain in minutes, forcing the team to huddle in tents for hours or even days, their carefully planned schedule at the mercy of the elements. The infamous summer swarms of black flies and mosquitoes are a relentless torment, requiring head nets and constant movement to maintain sanity. The sheer physical exertion of hiking across the uneven, glacially scoured terrain is draining, each step requiring focus to avoid a turned ankle or a nasty fall. Yet for all these hardships, the triumphs are profound and deeply personal. The moment a researcher splits open a rock to reveal a perfect zircon crystal glinting in the light, a tiny time capsule ready for analysis, is a thrill that fuels years of patient work. The camaraderie that forms around a campfire at the end of a long, cold day, sharing a simple meal while discussing the day's findings under the shimmering glow of the aurora borealis, creates bonds that last a lifetime. These expeditions are a physical and intellectual pilgrimage, a direct continuation of the human quest for understanding that has driven explorers for centuries. They return home not just with bags of priceless rocks, but with a renewed sense of purpose, having stood on the oldest ground and touched the deep time that it holds, ready to decode its secrets and share them with the world. The journey of discovery doesn't end when a geologist returns from the field with a precious sample of the Acasta Gneiss. In many ways, it's just beginning. The real magic of unlocking 4 billion years of history happens back in the laboratory, where a stunning array of high-tech instruments acts as a translator for the silent stories locked within the rock. These aren't your typical magnifying glasses. We're talking about machines that can pinpoint individual atoms and map mineral structures at a scale smaller than a wavelength of light. The process starts not with the rock itself, but with its context. Before a single hammer ever strikes the outcrop, scientists use satellite imagery and high-altitude aerial photography to create a broad-scale geological map of the entire region. This big-picture view helps them understand how the Acasta Gneiss fits into the larger puzzle of the Canadian Shield, identifying different rock units and major geological structures from above. Then, for a closer look, they deploy drones equipped with high-resolution cameras and even LiDAR sensors. These drones fly precise grid patterns over the site, capturing millions of data points that are stitched together into incredibly detailed 3D digital models of the terrain. This allows researchers to study the outcrop's size, shape, and relationship to the surrounding landscape from the comfort of their office, minimizing physical impact on the fragile site and helping them plan the most effective and least disruptive sampling locations. Once a sample is selected and carefully collected, the true analytical symphony begins. The first step is often preparing a thin section, a process that is both an art and a science. A small slice of the rock is cut with a diamond-edged saw and then ground down on a lapidary wheel until it is literally thinner than a sheet of paper, just 30 microns thick. At this minuscule thickness, light can pass through most minerals. This translucent sliver is mounted on a glass slide and placed under a petrographic microscope, a powerful tool that uses polarized light. When light waves pass through the crystalline structure of the minerals, they interact in unique ways, producing a dazzling array of interference colors that act like a fingerprint, allowing geologists to instantly identify the mineral types, see how they interlock, and observe textures that reveal the rock's complex history of heat, pressure, and deformation. It's under this microscope that researchers get their first intimate look at the rock's fabric, spotting those all-important zircon crystals that will become the key to dating the sample. To read the atomic clock inside those zircons, scientists turn to one of the most powerful tools in all of geology, the sensitive high-resolution ion microprobe, or SHRIMP. This is a type of mass spectrometer that operates on a mind-bendingly precise scale. A sample, often a grain of zircon smaller than a speck of pepper, is placed in a vacuum chamber. The instrument then bombards it with a focused beam of charged ions, which literally knocks atoms off the surface of the crystal. These ejected atoms are ionized and then accelerated through a powerful magnet. Because atoms of different elements have different masses, the magnet bends their paths by different amounts, effectively sorting them. Detectors at the end of this journey then count the number of atoms of each specific isotope, for instance, measuring the exact ratio of uranium-238 atoms to the lead-206 atoms they have decayed into. This process isn't just done once. The ion beam can be focused to an incredibly fine point, allowing scientists to make multiple measurements across growth zones within a single zircon crystal, potentially revealing not just one age, but a history of different geological events that affected it over billions of years. The SHRIMP doesn't just tell us the rock is old, it can tell a story of its long life. For even finer detail, researchers employ scanning electron microscopes and electron microprobes. These instruments use a focused beam of electrons to scan the surface of a sample. The interaction between the electron beam and the atoms in the mineral produces several signals, including backscattered electrons and characteristic X-rays. The backscattered electron image reveals variations in atomic density, creating a stark, black and white map that clearly shows the zoning and inclusions within a mineral grain. The X-rays are even more powerful. Each element emits a unique X-ray signature when excited by the electron beam. By measuring these signatures, the electron microprobe can create a detailed quantitative map of the chemical composition of the mineral, showing exactly where certain elements are concentrated. This is crucial for understanding the conditions under which the rock formed and metamorphosed, as the types and proportions of elements present are a direct record of the temperature and pressure it endured. Perhaps most exciting is the development of truly non-invasive techniques that leave the sample completely untouched. Portable X-ray fluorescence scanners, for instance, can be taken right into the field. A scientist can simply hold the gun-like device against the rock face, and within seconds it provides a basic chemical analysis of the elements present, helping to quickly identify rock types and mineral concentrations on the spot. Back in the lab, techniques like X-ray computed tomography, similar to a medical CT scan, can create a 3D internal model of a sample without ever cutting it open. These technological advancements represent a quiet revolution in geoscience. They allow us to be both thorough and respectful, extracting a phenomenal amount of data from a vanishingly small amount of material. Every precise measurement, every elemental map, and every isotopic ratio is a sentence translated from the rock's ancient language, building a chapter in the biography of our planet that was utterly inaccessible until these remarkable tools gave us the eyes to see it. The discovery of the Acasta Gneiss didn't just add a new data point to the geological record. It sent a seismic shock through the very foundations of planetary science, forcing a dramatic rewrite of Earth's earliest chapters. For decades, the prevailing view of our planet's first 600 million years, the Hadian Eon, was one of relentless, uninhabitable chaos. This period, named for the Greek god of the underworld, was envisioned as a global magma ocean, a molten hellscape under constant bombardment from space, where any incipient crust was quickly shattered and recycled back into the seething mantle. The existence of a 4-billion-year-old rock, a substantial piece of stabilized continental crust, directly contradicted this hellish narrative. It provided the first tangible proof that the Hadean was not a singular, molten catastrophe, but a dynamic period where our planet was already undergoing a complex and surprisingly rapid transition towards order. The Acasta Gneiss became the key piece of evidence supporting the cool early Earth hypothesis, suggesting that the planet had cooled enough to form solid, long-lasting crust much sooner than anyone had dared to imagine, perhaps within just 150 million years of the solar system's formation. This revelation forced a complete re-evaluation of the timeline for crustal stabilization and the onset of plate tectonics, the great engine that drives our dynamic planet. Before this discovery, many models suggested that modern-style plate tectonics, with its subduction zones and moving continental plates, began much later, perhaps around 3 billion years ago. The Acasta Gneiss, however, is not a simple, pristine igneous rock. It is a metamorphic gneiss showing clear signs of having been buried, heated, and deformed by immense tectonic forces. This tells us that not only did stable crust exist 4 billion years ago, but that powerful, large-scale geological processes were already actively reshaping it. The rock's very fabric is a frozen snapshot of these primordial forces. Scientists are now fiercely debating what these early tectonic processes looked like. Was it a more vigorous, faster version of the plate tectonics we see today? Or was it a different mechanism entirely, perhaps a form of stagnant lid tectonics where the crust moved in smaller, more localized pulses? The Acasta Gneiss doesn't provide a simple answer, but it absolutely demands the question, pushing researchers to develop more sophisticated and varied models for how rocky planets evolve from their fiery births into worlds with continents and oceans. Beyond the mechanics of crust formation, the chemical signature locked within the rock's minerals offers breathtaking clues about the surface environment of the early Earth, and by extension, the potential for life. The original protolith of the Acasta Gneiss has a granitic composition, and forming granite requires the presence of water. This single fact is monumental. It implies that significant water was already present in the Earth's crust or interacting with it over 4 billion years ago, dramatically pushing back the timeline for a hydrosphere. This wasn't necessarily a world of rolling oceans as we know them, but it was certainly a wet world at some level, challenging the old picture of a completely desiccated, vaporized planet. The presence of water, combined with evidence of a stable, cool crust, opens a tantalizing window of possibility. If liquid water and stable rock were present, could there have been niches where the building blocks of life began to assemble? While the Acasta Gneiss itself contains no fossils, it paints a picture of a world that was becoming increasingly hospitable, moving away from a perpetual inferno toward a state where the prebiotic chemistry essential for life could potentially occur. It helps define the boundary between a purely abiotic world and one poised on the brink of a biological revolution. Ultimately, the story of the Acasta Gneiss is a powerful testament to the self-correcting nature of science itself. It stands as a permanent reminder that our understanding of the world is always provisional, a best-fit model based on the evidence available at the time. A single discovery, a solitary outcrop in the remote wilderness, can overturn decades of established theory and force an entire field to pivot and explore new, more exciting avenues of inquiry. This rock has moved the goalposts for the habitable Earth, suggesting that the conditions necessary for life may have arisen astonishingly early in our planet's history. It forces us to look at other rocky worlds in our solar system and beyond with new eyes, wondering if their timelines for cooling and stabilization might also be shorter than we think. The Acasta Gneiss is more than a rock. It is a catalyst for curiosity, a physical embodiment of scientific progress that challenges us to continually question explore, and revise our story of how we came to be here on this resilient and ancient planet. Beyond its immense scientific value, the Acasta Gneiss complex serves as one of the planet's most profound and immersive outdoor classrooms, a place where abstract concepts from textbooks transform into tangible, touchable reality. For a student of earth sciences, standing on this surface is the ultimate capstone experience, a moment where 4 billion years of theory suddenly clicks into place with visceral clarity. Here, the rock cycle is not a simple diagram in a book. It's a story written in the twisted, banded layers of the gneiss itself. You can run your fingers over the foliation and feel the direction of the immense pressure that once shaped it. You can see the different mineral compositions, the light feldspar and quartz alongside the dark hornblende, and understand firsthand how heat and force can separate and metamorphose original rock into something entirely new. It provides a masterclass in the enduring nature of continental cratons and the destructive power of subduction zones, offering a real-world contrast that makes the entire dynamic system of plate tectonics infinitely more comprehensible. The educational applications extend far beyond basic geology into the very heart of chemistry and physics. The principles of radiometric dating, often a challenging and abstract topic, become stunningly clear when you hold a piece of zircon extracted from this rock. Instructors can walk students through the entire process, from the initial concept of radioactive decay and half-lives to the incredible precision of the mass spectrometers used to measure the uranium-to-lead ratios. It connects the dots between nuclear physics and historical inquiry, showing how the predictable decay of unstable atoms serves as a perfect clock for dating our planet. Furthermore, the rock's chemical composition opens discussions about crystallography, the formation of silicate minerals, and the specific conditions of temperature and pressure that can be deduced from its mineral assemblage, blending chemistry and thermodynamics into a single, coherent field study. Recognizing that not every student can journey to this remote wilderness, educators and technologists have performed their own kind of magic, bringing the oldest Flaw to the world through digital innovation. High-resolution 360-degree virtual tours allow anyone with an internet connection to navigate the outcrop, zooming in to examine the intricate textures of the rock as if they were right there. University programs utilize detailed three-dimensional digital models created from drone and LiDAR data, enabling students to manipulate, measure, and analyze the outcrop from their laptops, practicing field mapping and sample selection in a virtual environment before ever setting foot in the field. These tools are not just substitutes for the real thing. They are powerful educational assets that allow for repeated, careful study and democratize access to a site that would otherwise be the exclusive domain of well-funded researchers and adventurers. This direct engagement fosters a much deeper and more personal connection to Earth's history than any textbook ever could. It transforms learning from a passive absorption of facts into an active process of discovery. The sense of awe that comes from confronting deep time in person is a powerful motivator, sparking curiosity that can define a student's academic and career path. It moves the timeline of our planet from a sterile series of dates into a relatable narrative, helping to contextualize humanity's place within that vast history. This connection is the bedrock of scientific literacy and environmental stewardship. When people feel a personal link to the ancient processes that shaped our world, they are more likely to appreciate its fragility and advocate for its protection. Preserving sites like the Acasta Gneiss isn't just about saving rocks for scientists. It's about safeguarding an irreplaceable educational resource that has the unique power to inspire the next generation of geologists, planetary scientists, and curious minds to keep looking down and wondering about the incredible story written beneath our feet. This growing recognition of the site's immense value brings with it a profound responsibility, the urgent need to protect it. The Acasta Gneiss has survived asteroid impacts and continental collisions, but it now faces a new set of vulnerabilities born from its own discovery. The very human curiosity that drives us to understand this place also poses a threat, whether through the innocent scrape of a boot, the well-intentioned but damaging act of taking a souvenir, or the cumulative erosion of increased foot traffic. Add to this the looming, large-scale challenge of a rapidly changing Arctic climate, which threatens to alter the very environmental conditions that have preserved the rock for so long, and the mission of conservation becomes a complex, multi-front effort. The primary strategy for protecting this irreplaceable resource is one of managed access. Unlike a national park designed for high visitation, the Acasta Gneiss complex is treated more like a fragile archaeological dig or a scientific cleanroom. There are no paved paths, no informational kiosks, and no facilities for visitors. Access is intentionally not promoted to the general public, and those who do make the journey, primarily researchers, are required to obtain permits that outline strict protocols for conduct and sampling. This isn't about exclusion. It's about recognizing that some forms of knowledge require solitude and minimal disturbance to be properly studied and appreciated. The monitoring of the site is a continuous and evolving process. Scientists themselves have become its most vigilant guardians, using the very same advanced tools they employ for research to track its condition. High-resolution satellite imagery is used to observe the broader region for any signs of change or potential human impact from afar. More directly, each scientific expedition now includes a photographic and LiDAR documentation mission, not just of their new sample sites, but of the entire outcrop. By creating a precise, year-over-year, three-dimensional digital record, they can monitor even the most minute changes to the rock's surface, tracking natural weathering rates and ensuring that no unauthorized sampling or damage has occurred between visits. This creates a living, digital archive of the site's condition, a baseline against which any future alteration can be measured and addressed. Perhaps the most critical and successful aspect of the conservation model is the deep and respectful collaboration with the Tlicho and Dean communities. Their stewardship of this land for millennia provides an invaluable long-term perspective that complements the scientific snapshot. Indigenous rangers often participate in or help facilitate research expeditions, bringing their unparalleled knowledge of the land, its weather patterns, and its rhythms. This partnership ensures that conservation efforts are not imposed from the outside but are developed collaboratively, respecting cultural protocols and sacred values. It means that decisions about where and when to conduct research are made together, ensuring that scientific inquiry does not inadvertently disrupt hunting routes, sacred areas, or seasonal patterns of wildlife. This fusion of traditional knowledge with Western scientific practice creates a far more robust and culturally sensitive conservation ethic, one that protects the rock not just as a geological specimen, but as an integral part of a living landscape and cultural heritage. This collaborative approach directly informs the ongoing ethical debate that lies at the heart of conservation here, the balance between scientific collection and physical preservation. Every time a geologist takes a hammer to the Acasta Gneiss to remove a sample, they are, in a very small way, damaging the very thing they have come to study. It is a necessary paradox, the knowledge gained from analyzing that sample in a lab, determining its exact age, its formation temperature, its chemical clues about the early atmosphere, is irreplaceable and can often only be obtained through destructive analysis. The ethical framework that has evolved is one of minimalism and maximum yield. researchers are expected to take the absolute smallest sample necessary to answer their specific questions, and they are strongly encouraged to share their subsamples with other laboratories around the world to minimize the total amount of material removed. There is a growing repository of Acasta Gneiss samples in museum and university collections, intended to be a resource for future generations of scientists with more advanced technology, reducing the need for future expeditions to collect new material. The goal is to ensure that every single gram of rock that is removed provides a megaton of understanding, justifying the tiny, permanent scar left behind. Ultimately, the conservation of the oldest floor on Earth is about more than protecting a rock. It is about safeguarding a legacy. It is a commitment to future generations, both the scientists who will have even more powerful tools to interrogate its secrets, and the indigenous communities for whom this land remains a spiritual anchor. It is an acknowledgement that some wonders of our world are so rare and so profoundly informative that they deserve our utmost care, not for our sake alone, but for the sake of the human curiosity that will continue long after we are gone. By acting as conscientious custodians today, we ensure that this 4-billion-year-old chronicle remains an open book, its pages intact and its story still being patiently decoded for all the centuries to come. While the physical journey to the Acasta Gneiss is a profound experience, it's a pilgrimage realistically available to only a handful of researchers and adventurers each year. But what if you could kneel down and examine the intricate, swirling patterns of that 4-billion-year-old rock from your living room, classroom, or local library? This is no longer a futuristic fantasy. It's the powerful reality of virtual exploration, a technological revolution that is democratizing access to our planet's deepest history. Advanced digital tools are now tearing down the barriers of remoteness and inaccessibility, transforming this isolated outcrop in the Canadian wilderness into a global classroom and a limitless research lab. Through the magic of high-resolution photography, three-dimensional laser scanning, and immersive virtual reality, scientists and educators are building perfect digital twins of the entire site, allowing anyone with an internet connection to embark on their own voyage of discovery across the oldest floor on Earth, fostering a connection to deep time that was once impossible for all but a select few. The process of creating these breathtaking virtual experiences begins long before anyone boots up a headset. It starts in the field with a suite of sophisticated data capture technologies. Teams will often use drones equipped with high-resolution cameras to fly precise, overlapping grid patterns over the outcrop, capturing thousands of individual photographs. Through a process called photogrammetry, powerful computers then analyze these images, identifying common points and stitching them together into a highly detailed and accurate three-dimensional model. For even greater precision, researchers employ terrestrial laser scanners. These ground-based units emit millions of laser points, measuring the exact time it takes for each beam to reflect back from the rock surface. This creates a point cloud, a massive dataset of precise spatial coordinates that defines the outcrop's geometry down to the millimeter. The photogrammetry provides the realistic color and texture, while the laser scanning provides the exact shape and scale. Fused together, they birth a digital replica so faithful it can be used for serious scientific measurement and analysis, all without ever touching the physical rock. These digital assets then become the foundation for a multitude of accessible experiences. For the casual learner, this might mean an interactive online portal where you can zoom, pan, and rotate around the entire outcrop, clicking on hotspots that reveal information about specific mineral types, geological structures, or the techniques used to date the rock. For a more immersive experience, virtual reality applications transport you directly into the landscape. Donning a VR headset, You can literally stand on the virtual tundra, hear the wind, and kneel down to examine the banding of the gneiss up close, with a digital field guide in your hand explaining what you're seeing. Museums are increasingly incorporating these models into their exhibits, offering touchscreen displays where visitors can digitally hold and rotate a sample of the Acasta Gneiss, peeling away layers to see its internal structure. These aren't just videos or pictures, they are interactive, exploratory tools that empower user-driven discovery, making the awe of deep time tangible for a global audience. Beyond public education, this virtual paradigm is revolutionizing the very practice of geological research. In the past, a scientist in Japan or Europe who wanted to study the Acasta Gneiss would need to secure significant funding, travel for days, and collect a physical sample, a process that is costly, time-consuming, and inherently damaging to the site. Now, that same researcher can download a hyper-realistic 3D model and conduct a huge portion of their work remotely. They can take precise measurements of mineral grain sizes, map the orientation and complexity of folding in the gneissic banding, and even conduct virtual field trips with colleagues from around the world to collaboratively analyze a feature in real time. This drastically reduces the need for physical sampling, aligning perfectly with modern conservation ethics. It allows for the continuous study of the site's delicate surface over time, monitoring subtle changes from erosion or weathering, all while preserving the integrity of the original for future generations. Digital technology is not replacing the field geologist. It is amplifying their reach, enabling more science with less impact, and ensuring that this priceless resource remains as undisturbed as possible for centuries to come. Perhaps the most profound impact of this digital shift is its power to foster truly global and collaborative stewardship. By making the site virtually accessible, it ceases to be a distant secret and becomes a shared human heritage. A student in Brazil, a teacher in India, and a retired engineer in Norway can all share the same experience of visiting the oldest Flaw, creating a worldwide community of people who feel a personal connection to its preservation. This broadened base of appreciation is the strongest possible argument for its continued protection. Furthermore, these detailed digital archives act as a permanent insurance policy against loss. Should a rockslide, a forest fire, or the slow creep of climate change ever alter the physical outcrop, its perfect digital twin will remain forever preserved, a lasting record of its state at a specific moment in time. This fusion of cutting-edge technology with ancient geology ensures that the story of the Acasta Gneiss, a narrative 4 billion years in the making, will not only be protected but will be actively read and appreciated by everyone, everywhere, forever. Of course, a discovery as profound as the oldest Flaw on Earth naturally attracts its share of tall tales and speculative theories, and it's crucial to separate the hard-won scientific facts from the captivating but misleading fiction that often circulates. One of the most persistent myths is the idea that these rocks have remained completely unchanged, a perfect time capsule frozen in a single moment from 4 billion years ago. While their age is accurately measured from their initial crystallization, the reality is far more dynamic and interesting. As we've seen, the Acasta Gneiss is a metamorphic rock, meaning it has been profoundly altered by immense heat and pressure over its long history. Its beautiful banding is direct evidence of this transformation. It tells a story of endurance and adaptation, not static preservation. It hasn't been frozen in time, it has lived through time, recording every major geological event it has witnessed. Understanding this distinction is key. We're not looking at a pristine snapshot but a deeply etched and complex biography, which in many ways is even more valuable to scientists. Another common area of speculation involves leaping to extraordinary, often extraterrestrial, explanations for the rock's origin or composition. You might hear theories suggesting it is a fragment of another planet, a piece of ancient alien technology, or evidence of some lost, hyper-advanced civilization. While these ideas make for compelling science fiction, they ignore the far more incredible reality that the natural geological processes of our own young planet are entirely sufficient to explain everything we see. The mineralogy of the Acasta Gneiss, while ancient, is not exotic. It is composed of familiar minerals like feldspar, quartz, and hornblende, all of which form through well-understood terrestrial processes. There is no isotopic or chemical evidence within the rock that requires an otherworldly explanation. The true wonder lies in the fact that the ordinary, grinding mechanics of planetary formation and evolution, given enough time, can produce something so extraordinary. The lesson here is that a rigorous, evidence-based explanation, though it may seem less glamorous, is almost always more astonishing than any fiction. There's also a tendency to oversimplify the dating process itself, leading to a misconception that the 4 billion-year age is a single, absolute number carved in stone. In reality, this figure represents the careful, statistical work of analyzing numerous zircon crystals from multiple samples, resulting in a cluster of dates that converge around that ancient mark. Scientists don't claim the rock formed on a specific Tuesday 4 billion years ago. They present a robust and heavily supported age range. Furthermore, some of the zircons found within the gneiss can show slightly older or younger dates, reflecting the complex history of the rock. Perhaps a zircon that formed earlier was incorporated into the magma, or a later thermal event partially reset its clock. This complexity isn't a weakness in the science, it's a strength, demonstrating the meticulous care and multiple lines of evidence required to build such an irrefutable case. It's a conclusion built on a mountain of data, not a single measurement. Finally, it's important to address the myth of its utter uniqueness, the idea that this is the only place on Earth where such ancient history is written. As we discussed with comparisons to Greenland and Australia, the Acasta Gneiss is the oldest known intact rock, but it is part of a broader family of Hadean-era remnants. The Jack Hills zircons in Australia, for instance, are individual minerals that are even older, telling us that crust formation began earlier than the Acasta rock itself. This doesn't diminish its status, instead, it places it in a richer context. The Acasta Gneiss isn't a solitary, inexplicable anomaly. It is the flagship example, the best preserved piece of a puzzle that is being assembled from sites across the globe. Dispelling these myths isn't about shutting down curiosity, it's about channeling it productively. By clearing away the sensationalism, we can better appreciate the authentic, evidence-based marvel of this place, a resilient piece of our planet's foundation that tells a true story more compelling than any fiction. The quest to understand our planet's first chapters is accelerating, driven by new technologies and bold interdisciplinary collaborations that promise to peel back even more layers of this 4 billion-year-old mystery. One of the most exciting frontiers is the development of microanalytical techniques so precise they can analyze isotopes and elements within individual mineral grains at a scale previously unimaginable. Imagine a next-generation ion microprobe that doesn't just measure a zircon's age, but can map the distribution of specific trace elements within its microscopic growth zones. These subtle chemical variations act like an ancient weather report, potentially revealing fluctuations in the temperature of the primordial oceans or shifts in the composition of the early atmosphere from within the crystal itself. This could settle heated debates about whether liquid water was consistently present or if the early Earth yo-yoed between frozen and molten states. Another major focus is the search for biosignatures, not fossils, but the chemical ghosts of life's earliest precursors. The challenge is that any organic molecules would have been utterly destroyed by the intense metamorphism that created the gneiss. However, scientists are developing ingenious methods to look for indirect evidence. They are examining the ratios of different isotopes of carbon, sulfur, and iron locked within the most pristine mineral inclusions. Certain fractionations of these elements are heavily favored by biological processes. Finding such a signature, even in a metamorphosed rock, would be a monumental clue that prebiotic chemistry was already advancing on the Hadian Earth. It's a forensic investigation on a planetary scale, searching for a chemical whisper of life in a rock that has been screaming its geological history for eons. To access even deeper, untouched geological records, researchers are planning ambitious drilling projects. The outcrops we see at the surface have been weathered and altered by billions of years of exposure. By using specialized rigs to extract deep core samples from the heart of the craton, geologists hope to reach rock that has been sealed away from the elements, preserving chemical and textural details that have been erased at the surface. These pristine cores could reveal a more complete story of the rock's formation and its subsequent journey, offering an unobscured window into conditions we can only currently guess at. This is akin to moving from examining a weathered, ancient manuscript to unsealing a perfectly preserved scroll from a time capsule. The research is also expanding beyond Earth, becoming a critical reference point for planetary science. NASA and other space agencies are intensely interested in what the Acasta Gneiss can tell us about the early histories of Mars and Venus. These rocky planets formed from the same stellar nursery as Earth and likely had similar violent beginnings. By understanding the processes that allowed Earth to cool, form a crust, and potentially become habitable so quickly, we can create better models for how and why our planetary neighbors diverged onto such different paths. The ancient minerals of the Acasta Gneiss serve as a calibration point for interpreting data from Martian rovers and future missions to Venus, helping us recognize the geological fingerprints of a world that might have once been capable of supporting life. Ultimately, the future of Acasta research lies in tearing down the walls between scientific disciplines. The most exciting questions will be answered not by geologists working alone, but by teams that include astrobiologists, organic chemists, climate modelers, and computational scientists. Together, they can build sophisticated digital models that simulate the entire early Earth system, from mantle convection to atmospheric composition, and then test those models against the hard data provided by the ancient rocks. This holistic approach transforms the Acasta Gneiss from a static subject of study into a dynamic key, one that is continually unlocking new doors in our understanding of planetary formation, the origins of life, and our own place in the cosmos. The next decade of discovery promises to be even more revolutionary than the last, as we learn to listen more closely to the subtle stories still waiting to be told by the oldest Flaw on Earth. That profound sense of connection to deep time is not just an abstract concept for those who have made the journey. It's a deeply personal, often life-altering experience that reshapes one's entire perspective. Scientists who have dedicated their lives to studying these rocks often speak of a moment of startling clarity that occurs not in the lab but in the field. One geologist described the feeling of sitting on the outcrop at the end of a long day, the midnight sun casting long shadows across the gneiss. He had just spent hours meticulously collecting samples he would later date with million-dollar machines. But in that quiet moment, the data faded away. He said it felt less like he was studying an object and more like he was in conversation with an elder, one whose memory stretched back to the very beginning and whose silent presence was a gift of unimaginable perspective. For these researchers, the rigorous science of isotopes and crystallization temperatures doesn't diminish the wonder, it deepens it, adding layers of understanding to the overwhelming awe. This emotional resonance extends to visitors from all walks of life who are drawn to this remote place. A writer who traveled to the site described an unexpected wave of emotion, a feeling not of smallness but of belonging. She had anticipated feeling insignificant against the 4-billion-year timeline, but instead felt intricately woven into a continuum far grander than her own life. The rock, in its immense and patient existence, became a mirror reflecting back her own fleeting but precious moment in the story. Another adventurer spoke of the strange comfort he found there. In a world often dominated by urgent, human-made crises, the unshakable stability of the ancient Flaw offered a form of solace, a reminder that the planet has endured cataclysmic changes and will continue to do so long after our current concerns have faded. This shift in perspective is a common thread. The encounter acts as a recalibration of the soul, quieting the noise of daily life and amplifying the signal of our place in the cosmos. For Indigenous elders from the communities who are the traditional guardians of this land, the connection is of a different nature, one that has been nurtured over countless generations rather than discovered in a single expedition. An elder might gently place a hand on the cool rock and speak not of billions of years, but of the long-ago time when the world was still being shaped. In their view, the rock is not an inanimate object to be studied, but a relative, an ancient being that holds the memory of the people and the land. This perspective doesn't conflict with the scientific narrative. Instead, it offers a parallel way of knowing that is rooted in relationship and responsibility. Where a scientist sees a datable mineral, an elder might see a teaching stone, a place where young people are brought to learn about perseverance, respect, and the importance of living in balance with a world that is much older and wiser than we are. This wisdom underscores that our connection to deep time isn't just intellectual, it's also spiritual and ethical, a call to humility and stewardship. These powerful, multifaceted reflections reveal a beautiful and essential truth, that the journey to understand our planet's past is not a purely empirical one. It is a deeply human endeavor that lives at the intersection of data and wonder, analysis and awe. The encounter with the oldest Flaw challenges the artificial boundary we sometimes erect between science and spirituality. One is a method for understanding the mechanics of the universe. The other is a framework for understanding our place within it. Standing on that ancient rock, both approaches converge into a single, overwhelming experience of insight. It invites us to hold two thoughts in our minds at once: the precise, incredible knowledge of the radiometric clock that ticks within the zircons, and the humbling, emotional recognition of our brief, beautiful moment to be a conscious part of its story. This synthesis doesn't weaken either view. It empowers a more complete and meaningful connection to the history we are all a part of, encouraging us to walk through our own lives with a greater sense of curiosity, responsibility, and grace. Capturing the essence of the oldest Flaw on Earth is a challenge that calls for more than just a scientific lens. It demands an artist's eye. The Acasta Gneiss, with its swirling bands of black and white, its polished surfaces etched by glaciers, and its rugged, timeless presence a visual narrative that is both starkly beautiful and profoundly ancient. Photographers and artists who journey to this remote corner of the world are not merely documenting a geological site. They are attempting to translate deep time into a single, powerful image, to convey a feeling that numbers alone cannot express. Their work becomes a vital bridge, connecting the analytical rigor of science with the emotional, visceral response that this landscape evokes in anyone who encounters it. The artistic approaches to this subject are as varied as the rock's own complex history. Some creators are drawn to the macro view, using specialized lenses to explore the intimate universe within the stone. In these close-up shots, the gneiss transforms into an abstract painting, a chaotic yet harmonious dance of mineral crystals. You can see the delicate, needle-like structures of hornblende, the chunky, porcelain-like grains of feldspar, and the tiny, resilient zircons glinting like diamonds trapped within the matrix. These images reveal the rock's incredible texture, telling a story of immense pressure and slow, patient recrystallization that is literally etched in stone. Conversely, other artists pull back to capture the grand, sweeping aerial views. From above, the outcrop reveals its true scale, a vast expanse of gray and pink rock emerging from a mosaic of sapphire blue lakes and dark green spruce forests. Drone footage can sweep across this primordial canvas, showing how this ancient heart of the continent shapes the entire surrounding landscape, its enduring stability defining the very topography of the North. Working in this environment, however, is a monumental test of skill and patience. The first and most constant challenge is the light. Located near the Arctic Circle, the site experiences extreme variations in daylight throughout the year. In the summer, the photographer is blessed with the golden, low-angled glow of the midnight sun, which casts long, dramatic shadows that accentuate every groove and ridge in the rock, but must also contend with a sun that never sets, creating a flat, overcast light during the day. The winter offers only a few precious hours of dim, blue-hued daylight, but it also brings the possibility of capturing the rock dusted with snow, its stark patterns softened by a blanket of white, all under the ethereal glow of the aurora borealis. Then there is the weather, which can shift from perfectly clear to a blinding, horizontal snow squall in a matter of minutes, forcing artists to protect their delicate equipment from moisture and frigid temperatures that can drain batteries in seconds. Every shot is hard-won, a product of meticulous planning, relentless adaptability, and a willingness to wait for the perfect moment when the elements align to reveal the land's true character. The goal of all this effort transcends creating a beautiful picture. It is about evoking the emotional resonance of the place. A successful photograph of the Acasta Gneiss does more than show you what the rock looks like. It makes you feel its age, its silence, and its immense, patient presence. It might be an image of a single, gnarled tree clinging to a crack in the bedrock, its struggle for life highlighting the rock's utter permanence. Or it could be a time-lapse of the stars wheeling overhead through a crystal-clear Arctic night, the dizzying motion of the cosmos contrasting with the utterly motionless, ancient floor below. Filmmakers can use sound, the howl of the wind, the crunch of boots on gravel, the profound silence, to build an immersive experience that transports the viewer to that remote wilderness. Through these artistic choices, the cold, hard data of 4 billion years is transmuted into a sensory experience that can inspire awe and curiosity in a global audience, many of whom will never have the chance to make the physical pilgrimage themselves. This fusion of art and science creates a powerful feedback loop that enriches our understanding from both directions. The artist's unique perspective can often reveal patterns or details that a scientist, focused on sampling and measurement, might overlook. The way light catches a particular mineral alignment or the way erosion has sculpted a specific form can provide intuitive insights into the rock's history. Conversely, the scientific context gives the artist's work deeper meaning and authenticity. Knowing that the beautiful pattern they are photographing is a record of continental collisions and the birth of the crust adds a layer of narrative power that elevates the image from a simple landscape to a historical document. Together, they create a more complete and compelling portrait of this incredible place, ensuring that its story is not only understood by the mind but also felt by the heart, preserved not just in scientific papers but in the shared cultural heritage of our awe for this ancient planet. But this journey doesn't have to end when the video does. The story of the oldest Flaw on Earth is one we can all actively explore together, turning a moment of passive watching into a hands-on adventure that deepens your connection to this incredible piece of our planet's history. Imagine being able to test your newfound knowledge not with a stressful exam, but with a fun, interactive quiz that feels more like a game. We've created one that you can access right now, linked in the description below, where you can guess the age of different geological formations, identify minerals from close-up images, and see how your understanding of deep time stacks up. It's a chance to challenge yourself and maybe even surprise yourself with how much you've absorbed. For those who feel the pull of that remote Canadian landscape but know a physical journey isn't possible, technology offers an astonishing alternative. We've also included a link to a breathtaking, high-resolution virtual tour of the Acasta Gneiss outcrop. This isn't just a static photo, it's a fully immersive 360-degree experience. You can pan across the vast expanse of the Canadian Shield, zoom in to examine the intricate banding of the gneiss, and feel as if you're standing there in that profound silence, all from your own device. It's the next best thing to being there, a digital passport to deep time that allows you to explore at your own pace and satisfy your curiosity about every crack and contour. We also want to hear from you and learn together. In the comments, we're posing a question to spark a conversation. If you could ask one question to a scientist studying the Acasta Gneiss, what would it be? The most thoughtful and intriguing questions will be collected and put to a geologist in a follow-up video, making you a direct part of this ongoing discovery process. And for a more visual expression, we're running a poll asking what aspect of Earth's ancient history fascinates you the most: the violent formation of the crust, the mysterious origins of life, or the powerful forces of plate tectonics. Your vote helps guide the topics for future videos, ensuring we're exploring the mysteries that you are most passionate about. To take your exploration even further, the description is packed with resources. You'll find links to scientific papers for the truly curious, a list of documentaries that dive into other ancient wonders around the world, and even a guide to some of the most user-friendly geology apps that can help you identify rocks in your own backyard. This transforms your everyday surroundings into a potential field site, connecting the epic scale of billions of years to the very ground beneath your feet. By clicking, exploring, questioning, and sharing, you become more than just a viewer. You join a global community of learners and explorers, all united by a sense of wonder about our planet's incredible story. This is your invitation to not just learn about history, but to actively engage with it. Yet the story told by these ancient stones is not one of a static, unchanging world, but rather a dynamic chronicle of profound environmental shifts written in the language of chemistry and mineralogy. The Acasta Gneiss, for all its incredible age, is not a closed book on Earth's primordial climate. It is a foundational chapter that helps us decipher the entire volume of our planet's climatic history. By applying incredibly sensitive analytical techniques to these most ancient of rocks, scientists can begin to reconstruct the conditions of an atmosphere that existed before oxygen was even a major component, piecing together a picture of the world as it was, not as we know it today. The key to this paleo-detective work lies in the subtle, atomic-level clues that were locked into the rock as it formed and were miraculously preserved through its long, turbulent history. One of the most powerful methods involves analyzing the ratios of different isotopes of oxygen trapped within the mineral structures of the gneiss. Oxygen atoms come in slightly different weights, known as oxygen-16, and the heavier oxygen-18. The proportion of these two isotopes that get incorporated into a growing mineral crystal is highly sensitive to the temperature at which the crystal formed. Think of it like a natural thermometer frozen in time. When scientists can isolate minerals that crystallized from water on the ancient surface, perhaps in a primordial ocean, they can measure this oxygen isotope ratio and calculate the temperature of that water billions of years ago. While the Acasta rocks themselves have been metamorphosed, complicating this signal, they provide a critical baseline. They tell us that very early on, Earth had cooled sufficiently from its molten beginnings to host liquid water, setting the stage for all the climatic processes that would follow. This data point is the anchor for the entire timeline of Earth's climate, the starting line from which all subsequent warming and cooling events would be measured. Beyond temperature, the chemical composition of the Acasta Gneiss offers startling hints about the very nature of the early atmosphere. The rock's original granitic composition required the presence of water to form, which in turn suggests that our planet had a hydrosphere much earlier than previously thought. But the type of minerals present also tells us what the air was like. The absence of certain iron-rich minerals that rust easily indicates that the atmosphere 4 billion years ago contained virtually no free oxygen. It was a reducing atmosphere, likely rich in gases like methane, ammonia, carbon dioxide, and water vapor. This is a crucial piece of the climate puzzle because the composition of the atmosphere directly controls the greenhouse effect, which regulates planetary temperature. A thick blanket of carbon dioxide and methane would have created a powerful greenhouse, one that was absolutely essential for a young sun that was about 30% dimmer than it is today. Without that potent mix of heat-trapping gases, the Earth might have remained a frozen snowball, and the story of life may never have begun. The Acasta Gneiss, therefore, provides physical evidence for the conditions that prevented a permanent global glaciation, highlighting the delicate balance that has always existed between our planet's atmosphere and its temperature. This long-term perspective is perhaps the most valuable gift that the oldest Flaw gives to modern climate science. By studying the incredibly slow, natural cycles of greenhouse gas fluctuation recorded in rocks spanning billions of years, scientists can establish a baseline for Earth's natural climate rhythm. We can see periods of extreme volcanism that pumped enormous amounts of carbon dioxide into the atmosphere, leading to intense warming, and we can observe periods where carbon was slowly drawn down and sequestered in rocks and sediments, leading to cooling and glaciation. The Acasta Gneiss represents the very beginning of this planetary heartbeat. It helps us understand the fundamental geological processes like rock weathering and volcanic outgassing that have regulated Earth's climate for eons. This deep time context is the only way to truly appreciate the unprecedented nature of the current anthropogenic climate change. The rate at which humans are releasing carbon dioxide into the atmosphere by burning fossil fuels is orders of magnitude faster than any natural process observed in the geological record. The oldest rocks remind us that while change is a constant for Earth, the velocity of the change we are driving is not. Ultimately, the silent, enduring presence of the Acasta Gneiss offers a profound lesson in planetary resilience and fragility. It has survived unimaginable upheavals, witnessing the planet transition from a toxic, airless world to the vibrant biosphere we know today. It demonstrates that Earth possesses powerful, slow-acting feedback mechanisms that have, over millions of years, corrected course from extreme climate states. However, this resilience operates on a geological timescale, not a human one. The climate challenges we face today will unfold over centuries, not millennia, and the systems we depend on, our agriculture, our cities, our coastlines, are vulnerable to rapid shifts. The ancient Flaw doesn't offer a promise that everything will be fine. Instead, it provides a sobering reference point. It shows us the incredible power of greenhouse gases to shape a planet's destiny, and it underscores our profound responsibility as a species that has now become a dominant geological force. By listening to the whispers from this 4-billion-year-old witness, we gain not just knowledge of where we came from, but crucial wisdom for navigating the future we are now creating. Truly understanding a rock that has witnessed 4 billion years of history requires more than just a geologist's hammer. It demands a symphony of scientific minds, each playing a different instrument to decode the planet's oldest melody. The Acasta Gneiss is far more than a geological specimen. It is a nexus where the fundamental questions of multiple sciences converge. To ask how life began, you must first understand the stage upon which it emerged, and that stage was set by the very processes that formed this ancient crust. This is why the most profound insights no longer come from isolated fields working in silos, but from vibrant, collaborative teams where geologists, chemists, biologists, and astronomers share data, challenge assumptions, and build a unified story of our planet's infancy that no single discipline could construct alone. At the heart of this collaboration is the search for life's origins, a quest that binds the geologist and the biologist in a common pursuit. A geologist can identify a rock's type and history, but it takes a biogeochemist to look for the faintest chemical ghosts of prebiotic activity within it. While the intense metamorphism that created the Acasta Gneiss would have destroyed any direct fossil evidence, these scientists hunt for more subtle biosignatures. They analyze the ratios of different isotopes of carbon and sulfur locked within the most resilient mineral grains. Life, as it processes elements, prefers the lighter isotopes. It finds them easier to work with. So, finding a skew in the ratio towards lighter carbon isotopes within a 4-billion-year-old rock could be a tantalizing, though hotly debated, hint that some form of primordial metabolism was already at work, manipulating chemistry on a molecular level deep within the Earth's crust or in its earliest oceans. The geologist provides the context, assuring the sample is pristine and correctly understood, while the chemist provides the tools to read its elemental language, together probing the very boundary between a living and a non-living world. Meanwhile, the analytical chemists are the master translators of this ancient archive, employing tools so precise they can detect elements at parts per billion levels. They use mass spectrometers to not only date the rocks but to inventory their trace element composition. The presence or absence of certain rare earth elements within the zircon crystals can act as a powerful diagnostic tool. For instance, the specific pattern of these elements can reveal the oxygen fugacity of the magma from which the crystal grew, essentially how oxidized or reduced the early Earth's environment was. This chemical data is critical for biologists and geochemists building models of the early atmosphere and ocean, painting a picture of a world that was likely devoid of free oxygen, but potentially rich in dissolved iron and other chemicals that could have fueled the earliest metabolic reactions near hydrothermal vents, long before photosynthesis revolutionized the planet. And then we look to the stars, where astronomers and planetary scientists provide the crucial comparative context. The Acasta Gneiss is our only direct evidence of Earth's first crust, but it is not the only example of planetary formation in the universe. Astronomers studying protoplanetary disks around young stars observe the very processes of dust accretion and planet building that eventually led to Earth. They create sophisticated models of planetary accretion, simulating the violent collisions and magma oceans that characterized the Hadian Eon. These models make predictions about the timing of crust formation and the composition of early planetary atmospheres, predictions that are then tested directly against the hard data provided by the Acasta Gneiss. Conversely, the existence of this 4-billion-year-old rock forces astronomers to revise their models, confirming that crustal stabilization on rocky planets can occur surprisingly quickly. This two-way street of inquiry enriches both fields, turning Earth's oldest flaw into a Rosetta Stone for interpreting data from Martian rovers or telescopic observations of exoplanets, helping us understand which aspects of our planet's history are unique and which might be universal steps in the evolution of habitable worlds. This interdisciplinary dance culminates in a holistic understanding that is far greater than the sum of its parts. A single finding from the Acasta Gneiss doesn't just answer one question, it sends ripples through multiple fields. A revised date for crust formation affects astronomical models of planetary cooling. A new analysis of water content in ancient zircons influences biological theories about where life could have originated. This collaborative spirit acknowledges a fundamental truth about nature. It does not organize itself into the neat departments of a university. The birth of a planet, the origins of an ocean, and the spark of life are not separate events but chapters in a single, continuous story. By tearing down the walls between disciplines, we are not just studying a rock. We are learning to read the interconnected narrative of our cosmic home, a story written in mineral, element, and light, waiting for a chorus of voices to finally bring it to life. The growing fascination with the Acasta Gneiss presents a beautiful dilemma. How do we share one of Earth's greatest wonders with a curious world without loving it to death? This isn't a site that can accommodate busloads of tourists or support the infrastructure of a typical national park. Its value lies in its pristine, untouched nature, a quality that is incredibly fragile and instantly diminished by the very footfalls of those who come to admire it. The challenge, therefore, is not to build a gateway for the masses, but to design a system of deeply respectful and highly managed access that prioritizes preservation above all else, transforming a visit from a casual sightseeing trip into a privileged educational pilgrimage. Looking to other World Heritage sites and protected areas offers a blueprint for what this could look like. Some of the most successful models operate on a permit-based system with very limited numbers. Imagine a scenario where only a handful of small, guided groups are allowed to visit the Acasta Gneiss each year, with applications reviewed well in advance. These wouldn't be casual tours, they would be led by trained geologists or indigenous knowledge keepers who can provide profound context, ensuring visitors understand they are walking on a sacred scientific and cultural treasure, not just an interesting rock formation. This approach mirrors the systems in place for ecologically sensitive areas like the Galapagos Islands or Antarctica, where the experience is intentionally curated to be educational, low impact, and unforgettable, rather than convenient or commercial. The concept of a visitor center also needs reimagining for such a remote location. Instead of a large building at the site itself, which would be impractical and damaging to construct, the gateway could be hundreds of kilometers away in Yellowknife. A state-of-the-art facility that could serve as the staging ground and educational hub, featuring immersive virtual reality experiences that allow anyone to visit the Outcrop, extensive exhibits with actual rock samples that can be safely handled, and mandatory orientation sessions for the few who earn a permit for the physical journey. This strategy keeps the overwhelming majority of the foot traffic and impact far from the delicate site itself, while still fulfilling the public's desire to learn and connect. All the educational benefits are provided without any of the physical cost. Strict, non-negotiable regulations would form the backbone of this managed access. The rules would be unequivocal. No sampling of any kind by visitors, a requirement to stay on designated paths if any are established at all, a pack-in, pack-out policy for all waste, and a complete ban on drones or any other equipment that could disturb the area without scientific authorization. These rules aren't meant to be punitive. They are a necessary covenant between the visitor and the planet, a solemn agreement to leave no trace in exchange for the profound privilege of presence. Enforcement would be built on a foundation of mutual respect and education, with guides and community monitors ensuring these protocols are understood and honored by everyone who sets foot there. Ultimately, the most sustainable model is one built on partnership, learning from the millennia of stewardship practiced by the Tlicho and Dean peoples. Their relationship with the land is not based on visitation, but on belonging. Integrating this wisdom means that decisions about access aren't made solely by tourism boards or park services, but by a collaborative council that includes scientists, government officials, and most importantly, Indigenous elders and community representatives. This ensures that the spiritual significance of the land is protected with the same vigor as its scientific value. It recognizes that some knowledge is gained through quiet observation and respect, not just through physical interaction. By weaving together the best of Western conservation science with ancient indigenous principles of guardianship, we can create a lasting legacy for the Acasta Gneiss, one where it remains a vibrant, living classroom and a sacred heart of the North, utterly untouched by the passage of all but the most respectful visitors, yet deeply appreciated by a global community that understands its priceless value. And so our journey across this 4-billion-year-old surface comes to a close, not as an ending, but as an invitation to see our world with new eyes. This ancient Flaw is far more than a record of the past. It is a living reminder of our planet's profound resilience and a testament to the power of human curiosity. From its violent birth in the Hadian Eon to its quiet endurance through countless millennia of change, this rock has witnessed the entire arc of Earth's story, a narrative of chaos giving way to order and destruction paving the way for creation. It connects us not just to the origins of our world, but to the fundamental processes that continue to shape it, offering a perspective that is both humbling and empowering. This voyage of discovery underscores a powerful responsibility that rests with all of us. The survival of such an irreplaceable treasure hinges on our collective commitment to stewardship, blending the precision of science with the wisdom of indigenous knowledge and the care of conscientious conservation. It challenges us to protect these fragile windows into deep time, ensuring they remain untouched for the generations of explorers, scientists, and dreamers who will follow. But our duty extends beyond preserving rocks. It calls on us to safeguard the sense of wonder that drives us to ask big questions, to seek understanding, and to cherish the mysteries that still lie waiting beneath our feet. As we step away from this primordial landscape, let's carry its lessons with us. Let it inspire a deeper reverence for the intricate systems that sustain our planet and a renewed commitment to learning from its long history. The story of the Acasta Gneiss is a powerful echo of our own place in the cosmos, a brief but brilliant moment in a timeline that stretches back billions of years. Thank you for joining this exploration into the very foundations of our world. We encourage you to share your thoughts and reflections in the comments below and to keep looking down, for the ground beneath you holds stories more ancient and awe-inspiring than we can ever fully